Thank you, everybody, and thank you for accommodating me. I'm afraid I can't be there in person today. So I wanted to talk a little bit about what I see as one of the central challenges that we still face in AI, which is how to explain the decisions that AI systems take. And I'm going to show you a particular example that I've been working on, which is in medical imaging, and show you really where we are and what still needs to be done. Okay, so let's first of all just remind ourselves how far we've already come in AI. And it's been an amazing journey over the last sort of 10 to 15 years. Incredible progress has been made in systems that can now match and even exceed human level performance. And indeed, the speed of which we are able to solve some of these very difficult problems like handwriting recognition, image recognition, through to more complicated problems like common sense understanding, generating code, the pace is accelerated only through time. And now almost every problem that we define can be solved quite quickly by these AI systems. So this is really it's an incredible achievement. And of course, underlying this technology is deep learning, which is based upon these very deep nonlinear systems, sort of loosely modeled on the brain as well. So the question, I think, really, which is very interesting, is though, can we, to some extent, explain how these systems might work, and possibly do we even need to understand that? The one thing also just to bear in mind, by the way, is that the speed of computation has been, of course, a huge factor in the progress that we've made so far. And just to give you some indication as actually how far we've really come, the basic architectures behind these systems haven't really changed in, I would say, 50 odd years. Yes, there's been the transformer, but fundamentally, I'm not sure that's necessarily the most important thing. You can still get very highly performance systems using more sort of standard recurrent architectures as well. But what has changed a lot is the speed of computation. So if you take, for example, an image here, like in the middle of a Cray 1 supercomputer from 1975, this was the fastest system in the world at the time. It cost around $40 million. And you compare that to, for example, an NVIDIA GPU chip of these recent years. It might take, for example, around maybe a month of training on one of the current GPUs to, say, train an image recognition model, something like that, high performing one. So one question might be, well, if I were to go back to that 1975 Cray 1 supercomputer, and I were to try to train that same image generation model, for example, so 1 month equivalent of a H-state 100, how long would it take the Cray 1 to do the training of that same system? Well, it might surprise you. So often when I ask this question, the audience, many people say, well, 1 month, it might now take, say, or it might have taken the Cray 1 maybe 100 years, something like that. People laugh to think that's kind of like a crazy, overestimate of how long it would take. The reality is probably closer to around 2 to 3 million years. Actually, it would take the Cray 1 supercomputer to train a simple, in today's sort of notation, if you like, a state-of-the-art, say, image recognition or generation system. So this kind of scale up of computer speed is really, it's very, very significant, and I think it's something that, in some sense, we easily forget. But where do we want to go with some of this? So currently, we have things like training data. We go through some complicated learning process. This results in some deep learning parameterized function. And then we have some kind of image, like, for example, this cat. And we want some output from the network to say, well, what is this? And in this case, it says with a 93% probability, this is a cat. So this might be fine, depending on your use case. But some people might say, well, actually, I don't just want a prediction. I want an explanation for that. Why did you come up with this prediction that this was a cat? Why not something else? When will it work? The system, when won't it work? How much can I trust it? And how can I correct an error? So that's kind of what we might like to have. So on the bottom here is this more aspirational setup where we might have the training data, some different learning process, and some explainable model, which would say, okay, I can tell you this is a cat because it has fur, whiskers, and claws, and it has these various features, etc. Then when a user has a particular task, they hopefully understand more about when the system might work and when it might not work. So, of course, there are different perspectives on this. Some people might say, hoping for a simple explanation from these very, very complicated models is really quite hopeless. And maybe it's not even necessary. Some people will say testing a system that it works, it's better than trying to explain it, particularly if that system is so complicated. So that's one viewpoint which some people have. Another viewpoint is that, well, yes, maybe that they are very complicated and it's difficult to get a full understanding, but perhaps we can gain some intuition about how these systems work by examining under what conditions, for example, the neurons deep inside these deep networks might fire. For example, we've learned from image systems that low-level features tend to be learned close to the input, and high-level features tend to be learned close to the output layer in these deep networks. And similar efforts are underway using mechanistic interpretability and things like LLMs, although I think that's also quite controversial as well. And an alternative viewpoint is that actually in some cases, the explanation for prediction is perhaps the only thing really that's of interest. In the sense that, for example, maybe you're interested in medical analysis and you want to understand what it is that's making the prediction. Is there something there, some mechanism that you can understand, which is explaining why patients, for example, are dying earlier than others, and that actually could then give you some insight into cause of the disease or the progress of the disease. Now, the problem is that many of the current approaches don't take interpretability into account when actually designing the model itself. They tend to do it only post-training, and I'll explain a little bit more about that. So this is a typical approach that is currently taken. You've got some trained vision system, and you then try to understand it by saying, okay, here's on the left a picture of a soup bowl. How can I perturb the pixels in this image to make it look even more like a soup bowl? So this is kind of perturbative gradient-based approaches. And the image on the second image is actually what comes up. And you could say this is not very clear or a good explanation visually as to why the left image is actually a soup bowl. Similarly, we have a stethoscope here and do another perturbative analysis, and we end up with the image on the right, and it's also very unclear, really, and it's not a very good interpretation of actually what's going on in the original image. So on these perturbative approaches tend to be rather unreliable. GradCam is another well-known and well-used method in convolutional deep neural networks to try to explain what's in the image making the prediction. And I won't go into details here, but this is also similarly challenging. It tends to result in very fuzzy explanations. So, for example, here, if you say, given this image, please tell me what in this image makes the classification Australian Terrier, and you get something reasonable, but it's fairly fuzzy down in the bottom right where the dog is. So it's not bad, but it's not great either. Indeed, there have been studies that suggest this challenge is not really just restricted to one or two approaches. Here's a paper from a couple of years ago that compared a whole host of different image post-training image interpretation mechanisms. And just to give you an understanding what's going on here, on the right column, this is the input image, and the next column along is the ground truth actually as to what's explaining that. So in this case, there are some fish here. This is where where and what the fish are, etc. Similarly, here's a frog. This is where the frog is. And there's a whole range of different methods here. Some of these gradient-based ones, some are other approaches as well. And none of them really nails it. Some of them doing better than others. So this polycam is not bad, but most of them are actually rather poor. And the conclusion from this paper was that actually none of the methods really worked particularly satisfactorily. So to my mind, this is a very difficult, challenging problem, and it's quite an important problem when you're thinking about how to use AI to explain decision making. And indeed, one of the challenges might be that explanations for why this has been difficult is that we're not building in the construction of the model an interpretability requirement. So let me give you an example where this might be important. So I've been working on a lung project. So this is part of a global charity who have collected a lot of CT scans about a very serious lung condition. And in a normal lung, your lungs, if you were to zoom in a small part of your lung, they look a little bit like this, where these are kind of sort of these holes here, if you like, between these tubes, this capillary, these tiny airways here, and these holes actually massively improve the gas exchange that's required for you to breathe. On the other hand, if you have a condition called idiopathic pulmonary fibrosis, these interstitial tissue here actually gets very stiff, it's fibrous, and actually this makes it extremely difficult for you to breathe. And people with this condition, unfortunately, don't tend to survive very long. So radiologists, they look at these CT scans and they visually can identify certain features in them that to them are predictive of the likely outcome for a patient. So they've got various terms for them. So for example, they call it honeycombing or ground glass. This is what they look like to them, reticulation, etc. There are about 6 or 7 of these established visual features that they look for to explain the likely outcome of the disease. Now, it's very interesting if we could find our own features in CT scans, not necessarily relying on what the doctors have found, but are there other things in these CT scans that we might be able to discover that would predict the outcome, say, of the disease or the prognosis for somebody? So in that sense, we are the only thing we're really interested in, or the main thing we're interested in, is actually an explanation, a visual explanation for the outcome of the disease. This data set is around 7,000 scans, which is quite a lot. It took about 8 years just to collect this data, so it's been a huge global effort. And what are we going to try to predict? We have to predict something when we're training our model. We're actually going to try to predict how long somebody will live. So if you try to predict other things like the amount of their lungs decline in terms of the volume that they're able to breathe, that didn't work very well. But the mortality, how long they're likely to live, was a much more robust endpoint for us to predict. One of the challenges that in this data set, over 70% of the patients are still alive at the time that that we ran our model. So this is so-called right-centered, and actually almost half of them have some missing clinical information as well. So you need to be thinking of practical ways to deal with the fact that if you're trying to predict the time of death, actually the majority of the patients haven't yet died. So, but there's still information in the fact that they survived a certain amount of time. We shouldn't just throw those patients away. If we did that, we'd throw away 70% training data. What we want to do is use the fact that we know they're still alive, even though they're not dead yet, and help us to train a prediction. So the standard approach to doing this is to use a Cox model, which is a survival analysis tool. And this is equivalent to a kind of ranking model. So the time of death of patient I is ranked according to, say, patient I would die before patient J, according to some probability distribution, which is given by the right. So pi is some network, a deep neural network. It takes input the image, a CT scan of patient I, and some clinical data as well, perhaps the age, what antifibrosis drugs they're on, and it calculates this probability using this formula, and then it trains, knowing the training data, that patient I did actually survive before longer than patient I died before patient J. We can adjust the parameters so that it matches well the ranking in the training data. This is kind of okay, but it's only a ranking model, and it doesn't really care about the absolute time of death. Cox has no concept of the absolute time of death, only the relative time of death. So what we did is we introduced a method to directly predict the time of death. And there are many ways to do this. We use a probability distribution, probability of time of death directly, which is a discrete Gaussian. You could use pretty much any distribution you like. So these takes in some kind of CT scan or gain of clinical input. It outputs two values, something like a mean and something like a variance. These are not actually means and variances in the discrete Gaussian, but they're kind of analogous. And we can use this to directly then train the prediction for when a patient dies. There's no need in this case for a Cox model, but one obvious question would be from you, how do you train this, because you don't know the time of death. I'm not going to go into the details here, but if you want, you can look at this paper that we had in medical imaging last year, and we explain a new way how to deal with the right censoring. It works very well, and it's different from the classical censoring approach in the statistics literature. And this method works well. We are actually able to predict our methods called centime in terms of the number of months error that we make in terms of the prediction. This is the number of months that somebody will die or die. The error in the number of months in predicting that they will die is actually smaller for our method than for any of the other methods in the literature. So it's as good as Cox as well in terms of producing the ranking, but it's much better in terms of absolute time prediction. But the problem is with this, this was a kind of convolutional deep neural network that we used to make the predictions. And then when we tried to use something like GradCam to explain these predictions, what is it in these long images is actually making this, say, poor outcome for patients, the results were very fuzzy. And this is, again, the common issue, how to interpret images in deep learning. And I was personally not very satisfied with these results. So let's just see if we can address how we can explain images better. So I'm not going to go into the details, but I'm just going to give you a sense of what we did, which is we tried to make a model which has got built into it an interpretability. So this is based upon how we think doctors look at your lungs. So they say, okay, this bit of your lung is fine, this is fine, this is fine, but this bit here doesn't look good, and this bit doesn't look good, and maybe this bit's not good, and that's not good. So it's, it doesn't matter how much, say, green stuff there is, they just ignore that, and they only focus on the bits that sort of concern them. So in other words, your outcome is dominated by the points which worry them, and these are really the only things that are particularly important to them. So what we're going to do is then try to make a model which will reflect that intuition from the doctors. So we break our 3D lung CT scan into a large number, around 25,000 32 by 32 by 32 cubes or cubelets. And for each cubelet, the deep neural network will predict a mortality value. And then what we do is, of all of these 25,000 cubelets, essentially we take the worst cublet, the cublet which predicts the lowest number of months for survival, becomes the overall patient mortality. And this is then used in the centime objective function to train an end-to-end deep neural network predictor. And we know this works because we can make some toy data with some synthetic long CT scans and place balls where we think that these are sort of bad fibrotic regions, and we can check that our mortality maps that we learn from this are actually accurate. And similarly, this method works very well. It has the lowest score in terms of error, in terms of months prediction of all the other methods. And most importantly, the predictions as to what it is in the lung images that's causing the bad outcome for patients is completely different to classical approaches based on things like GradCam and salience maps. On the right, you have a slice of the lungs, and this is the red means this is bad for you, green means it's good for you, according to Bradcam, saying it's a map. Whereas in our approach on the left, red means it's bad for you again, green means it's good. These are completely different. And according to the clinicians that we've spoken to, the images that we produce are much more aligned with their own intuitions as to what in these images is bad. Similarly, here's another example. Again, the same patient. We have a completely different prediction in terms of what it is in these lungs, which is actually causing a negative outcome. This is my final slide. And so the take-homes are really that finding plausible reasons why complex models take decisions is a very difficult problem, and it's certainly not been solved by previous approaches. And in my opinion, part of the problem is that most approaches, they train these complex models for some reason, for example, to predict class of an image, and only after training do they actually hope that they can find a way to explain the model. So what I've been arguing here is that in cases where interpretability is critical, for example, this lung imaging project, it's vital that you build models from the beginning that are inherently interpretable and not to rely simply on post-training visualization methods. And to demonstrate that that strategy can lead to useful results, I've shown you a model called Centene Maps, which has this interpretability baked in, and it learns biologically and clinically useful image-based biomarkers for this particular lung condition. Okay, I'll stop there. Thank you.
Thank you.